In this video, I'm going to give you a thorough introduction into sine waves with a particular focus on the three sine wave parameters and the results of selecting those parameters on the graphs of the sine waves. So here again, you see the formula for a sine wave. This is the complete formula, a sine 2 pi ft plus theta. And so what I'm going to do now is take a few moments to walk you through each of these three key parameters, a, f, and theta. Let's start with a. You can see that a is a single number, it's a scalar, that's multiplying this entire expression here. And what a does, what this amplitude factor does, is basically stretch on the y-axis. So it stretches up and down the entire sine function. And because the sine function goes positive to negative, the effect of a is actually to pull the positive parts up and pull the negative parts down. So here you see a sine wave where the frequency and the time and the theta are the same, and all I've done is change the amplitude from 1 to 2. So the frequency is the same, the exact timing is the same, so they peak at the same time, they have a trough at the same time, but a equals 2 gives us a higher energy, so more energy in this sine wave compared to this sine wave. All right, so that's the parameter a. Then we get to the parameter f, that is multiplying t in here. That's the important part, that it's multiplying the vector of time points. This 2 pi here is a scalar. It's like, you can think of it as a normalization factor. The important parameter is f, multiplying t inside the sine function. So here we have two different sine waves that have the same amplitude, the same time vector, the same phase, but different frequency. So this one is a frequency of twice this one, so it has twice as many cycles in the same period, so twice as fast. Or I guess you could say this is half as fast or twice as slow. So that is for frequency. Then we get to phase, and that is an additive parameter. So here is multiplication by an amplitude outside. Here is multiplication inside the sine function. And then we have the additive parameter, and that is called the phase, or sometimes in mathematics, it's also called the argument of the sine function, but I'm not going to use that term at all. I'm just going to be calling this the phase of the sine wave. So the phase of the sine wave is measured in radians, so it's a circular measure. It goes around the circle. You will learn more about what that means and how to quantify that later on in this section. And essentially, this phase shift parameter is just governing where the sine wave is when it crosses time equals 0. So it's basically like grabbing this whole sine wave and just shifting it to the right. So you're sliding it to the left or to the right. And that's really what the phase parameter does. So here you see two sine waves with the same amplitude, the same frequency, and the phases differ by pi over 2. So this one has a phase of 0, this one has a phase of pi over 2. And you can see that, the relationship between these two sine waves is just that, like you take this sine wave and you drag the whole thing to the right. You don't stretch it, you don't compress it, you just drag it to the right. Now, two sine waves with these parameters, 0 and pi over 2. I didn't just pick these totally randomly by chance. I picked these for a very important reason. These phase parameters of 0, which actually means you're just dropping this term, and plus pi over 2 are very important in data analysis. They are so important that we have given specific names to sine waves that have this phase parameter and this phase parameter. And those two names are sine and cosine. So when you see a sine wave that has a 0 phase parameter, that's called a sine. And if you shift it by pi over 2, then we call it a cosine. But you can see that it's really the same beast. It's the same mathematical object. They're just shifted a little bit. So this one's a cosine, this one's a sine. Cosine and sine are really important because they have a special property relative to each other, which is that they are orthogonal to each other. That means if you would correlate this signal and this signal, that correlation coefficient would be exactly 0. And you can already kind of see this visually. So this sine wave is going up and then down, and this sine wave, in that same time window, it goes down and then up. So the positive slopes here and cancel with the negative and the positive slopes here, and so on. When you learn more about the dot product and more about sine waves later on in this course, over the next like half an hour or so, then you'll learn more about why these two sine waves are so important relative to each other. Okay, so far I've introduced you to these three parameters of a sine wave. So amplitude, frequency, and theta in phase. So what I'd like to do now is show you a little MATLAB GUI, a little graphical user interface that I wrote to help understand what these parameters do, what effects they have on the resulting sine wave. So let's switch to this little GUI in MATLAB. So what you see here is a polar plot. So this is a circular plot, and this shows phase going around here. Remember I said that the phase parameter is measured in radians, so it's going around the circle here. And then we have the parameter amplitude, and that is the distance of this red circle away from the origin of this phase space, or this polar space. So notice what happens to the sine wave as I move this parameter around. So I'm going to click around here, and that's going to give me a different amplitude and a different phase. And actually what I think I'm going to do is try to keep the phase about the same, and I'm just clicking closer and closer to the origin, and the sine wave is getting more and more compressed because it's getting flatter. The amplitude is getting smaller. So now I'll try to keep the same phase. Maybe this is easier if I just go up the sine axis. So now I'm trying to keep the same phase here, and you can see in the plot that the sine wave is getting bigger, the amplitude is getting larger, but the phase isn't changing. Now what I'm going to do is keep the amplitude the same, but move this thing around the phase circle. So the amplitude is staying approximately 1, and the phase is shifting around the circle. And you can see, it looks like this thing is traveling along to the right. All right, and now we can keep this fixed, and with this bar, I'm going to change the frequency. So now notice that the amplitude is not changing, the height of the troughs and the peaks are not changing, and the phase also isn't changing. So at the value of the sine wave, where time equals 0, is always the same. It's always, this little nook here right just before it gets to the peak. That's staying the same as the frequency is increasing and decreasing. Okay, so I hope this gives you a little bit of a better intuition for the relationship between amplitude and phase and frequency.